Hi, this is David Follis, and this is our continuation of our video series on why WebSphere Application Server on zOS. With the value of System Z in the zOS platform established, it's now time to move on to an exploration of how WAS on zOS takes specific advantage of the functional attributes of the platform. This chart offers a kind of roadmap of the topics to be explored. The left side of the chart shows topics that are more high-level, topics that do some necessary stage setting prior to moving on to the topics on the right side of the chart, which focus on specific integration with platform functions. Earlier in this presentation, we spoke of WAS being WAS, but recall that the focus there was on the common and consistent open standard application specifications across all supported platforms. We made the point that below that open specification line, where the functional implementation takes place, there are platform-specific things going on. This naturally brings up the question of how different the administration of WAS is on zOS versus the other platforms. The question's perfectly reasonable and justified. To the extent possible, WAS administration skills should be transferable across all platforms. The good news is that to a large degree that's true. That's what this chart is indicating. Much is common across platforms. Some is different. The differences come in the closer to the platform you get. The chart progresses from the application layer on the top to platform-specific runtime construction at the bottom. Not surprisingly, there are no differences at the top. Differences appear as you move down the chart. Obviously, the construction of the runtime on zOS is different from, say, on Windows. The creation of the runtime on zOS requires certain zOS skills to run batch jobs to create the components. It's not difficult, but it is different from other platforms. The logging of WAS runtime activity is something that non-zOS administrators initially struggle with. WAS zOS by default makes use of the JES spool for its output. JES has a 134-character width limit, while logging on the other platforms does not have that restriction, so the look of the WAS zOS logging is a bit different. The information's the same, but the look is different. Version 8's high-performance extensible logging, or HPEL feature, allows for a completely consistent logging facility for WAS across all platforms. This chart is showing a brief summary of key enhancements to the product since the early days of version 4. The focus here is on zOS-related enhancements rather than general cross-platform enhancements to WAS. The reason why the message delivered on this chart is important is this. For those whose only experience with WAS zOS was based on the old version 4, which was released about a decade or so ago, that experience was likely to have been a bit disappointing. WAS zOS version 4 had its share of problems related to the product being very new and related to the product on zOS being considerably different from that on other platforms. This chart's designed to convey the message that WAS zOS has been subject to a considerable amount of functional enhancements over time. The enhancements related to zOS platform-specific function made the why WAS on zOS argument even stronger, since those enhancements were made to take even more advantage of the platform. Remember, this is in addition to the earlier message about WAS is WAS and application API commonality across platforms. And this chart does not include all the general WAS improvements related to new standards-based functions such as JPA or OSGI. Those are valuable functions, but they're not represented here because the focus of this chart was zOS-specific enhancements. This chart is showing the performance improvements seen in WAS over time with changes in two variables, the version of WAS zOS and the hardware platform on which the test was run. The trend is obviously upward. The end-to-end improvement is a factor of over 5 times better performance. Notice how the bars in the chart represent changes in either software or hardware, but not both at the same time. What the chart is showing is how overall performance is a function of both software enhancements as well as hardware enhancements. The hardware improvements are well documented on the IBM website for System Z hardware. Faster clock speeds, better cache design, and other processor and system design factors. The software improvements came in 3 forms. First, improved code path efficiency with certain parts of the WAS product, particularly the JPA code exercised by the DayTrader sample application. Secondly, improvements in the efficiency of the JVM, particularly in the area of the just-in-time or JIT compiler. And third, improvements in the JVM to take specific advantage of new processor instructions introduced in the Z10, Z196, and ZEC12 processors. As with any performance chart, this test was performed under controlled conditions with a specific sample workload with a specific system setup configuration. Performance results are a function of many factors, and your results may vary. The results shown on this chart are not a promise of performance gains and should not be taken as such. This chart should not be used for capacity planning. Other capacity planning tools for System Z are better suited for that role. This was a test of WAS zOS throughput performance under the specified test conditions. The test conducted measured achievable throughput when the CPU utilization was pushed to near 100%. The aggregate performance is a normalized measure of achievable throughput, with the leftmost bar in the chart serving as a baseline value of 1.0. Let's revisit the subject of the Java SDK. Earlier, we reviewed how the SDK was aware it was running on System Z and zOS, and how it had zOS-only extensions to take further advantage of the platform. Now let's see how the SDK relates to WAS zOS specifically. The first point is that the Java SDK is included with WAS zOS. That was not the case back in the early version 4 and version 5 timeframe, but it is true now. Packaging Java with WAS zOS is a good thing. It means the maintenance of the SDK is the responsibility of WAS zOS. So fix packs to WAS zOS carry with it any necessary fixes for the embedded SDK as well. That eliminates problems with mismatches between WAS and the underlying SDK. You may run WAS zOS servers as either 31-bit or 64-bit, and it's configurable by server. The same is true of the level of the SDK. WAS 8.5 comes with both SDK 6 and SDK 7, and that's configurable by server as well. One of the most common questions asked is, how much of WAS zOS is offloaded to the specialty engines? The answer most commonly given is, it depends. That's admittedly not a satisfying answer, but it is valid. Let's explore why it depends. The key consideration is what the Java workload is doing. A workload that involves relatively more processing within the JVM without exercising native platform functions will naturally use more Java. That will result in more offload. Contrast that with workload requests that spend relatively little time in the JVM but rather go immediately off to other data systems in zOS. In that case, relatively more WAS zOS native platform processing is taking place, and thus relatively less pure Java is taking place, hence less offload. We use the number range 50 to 80% offload to express this it depends nature of specialty engine offload for WAS zOS. At first glance, this chart looks wordy, but within the words are several key points that are important to understand with respect to applications and WAS zOS. The most important points are made in the highlighted box on the left side of the chart. Specifically that WAS is WAS, and applications are written to the standards, not the platform. Developers don't write applications for WAS zOS. They write applications for WAS in the open standards supported by that version of WAS. But there's a point here that must be understood. The throughput and efficiency expectations for the zOS platform are higher than for other platforms. The zOS platform is typically used for very high throughput and very high I/O applications. When an application is placed under high stress, any inefficiencies in the application design and coding are going to be surfaced as poor performance. It's just a simple fact. Poorly written code performs poorly when placed under high stress conditions. That's what we see time and time again when applications are moved to WAS zOS and appear to perform badly. It's not that WAS zOS is causing the application to perform differently, it's that the workload demands on WAS zOS are much higher than on other platforms where the application was unit or function tested. The inefficiencies in the code are amplified and the expected throughput is not achieved. We've seen time and again that when the application is analyzed and the inefficiencies corrected, the performance improves and WAS zOS is capable of going to very high rates of throughput. If an application is intended to be deployed on zOS under high throughput conditions, it's best to make sure the application is developed using good coding standards, with tight coding around heavily used functions. This is simple common sense, but sometimes common sense is overlooked when an application is being rushed through development up to production. Sometimes stress and throughput testing is taken out of the test plan to expedite the timeline. That's a shame because ultimately the project timeline is elongated when retesting is required to figure out why the application didn't scale. And if in that process WAS zOS is unfairly eliminated from consideration simply because it was the platform where the inefficiencies were surfaced, then you lose all the benefits of WAS zOS. WAS zOS has a unique application server design that separates request handling from application serving and uses WLM for classification and work routing. The control region, or CR, receives the inbound work requests, interacts with WLM for classification, then queues the work for execution by a servant region. The servant region, or SR, is where the application runs, and there may be one or more SRs available to do the work. SRs pull the work from the WLM work queue and execute. The CR has a JVM, each SR has a JVM. This is the design for any given application server. The WAS network deployment topology allows for one-to-many application servers. Two application servers clustered across LPARs in a parallel sysplex would imply the design above on each LPAR. The application server design for WAS on every other OS platform consists of a single JVM. The multi-JVM design you see above is unique to zOS because only zOS has zOS Workload Manager to interact with for work classification and placement. There are several things about this design that are of value. Multiple SRs behind a CR provide separate address spaces and separate JVMs for your applications. The loss of an SR does not necessarily imply the loss of your application. A surviving SR may pick up the work. This forms a cluster of application JVMs behind the CR. Application server CRs may then be clustered across LPARs. This forms two layers of application availability, the outer or horizontal cluster across LPARs and the inner or vertical cluster of SRs behind any given CR. Servant regions pull work from the WLM work queues, which means any given SR will not be overwhelmed with incoming work. SRs pull only the work they're able to consume. Temporary spikes in work are buffered on the WLM work queues. The number of SRs may expand either automatically by WLM or manually by you with modify commands. Multiple SRs mean more worker threads executing your application. The ability to expand and contract the number of SRs provides a form of dynamic capacity for applications within an application server. The previous chart indicated that the CR interacts with zOS Workload Manager to classify work. That means the CR is turning to WLM to assign a service class to the work request. A WLM service class is what provides the priority goal definition WLM uses to manage system resources. The WLM CB subsystem classification rules are used. All work received by WAS zOS application servers are classified, and all work will be assigned to a WLM service class. You have within your control the ability to differentiate work by WLM service class, which means you can indicate the relative priority of work by request. The spectrum of differentiation runs from one service class for all WAS work to different service classes by application server to different service classes per application or even function within an application. The most common approach is to use the CN classification rules to assign different service classes by application server. Applications are then deployed to servers based on knowledge of the service class assignment for the server. High priority applications are deployed in application servers with WLM service classes with high priority goals. Lesser priority applications to app servers with lower priority goals. Another approach, an approach that offers considerable granularity of control, is to use the WLM classification file to assign transaction class or TC values to individual requests received by the CR. Rules defined in WLM then map the TC value assigned to service classes and reporting classes. One of the most common uses of this is to assign different WLM reporting classes to work requests within the same application server. This allows WLM to collect usage information segregated by identified request, which then allows RMF to report on resource usage separately. This allows applications to be combined within the same application server, but still retain visibility to meaningful usage statistics per application. The next level of sophistication is to assign different WLM service classes. This allows different work requests to carry different service goals and thus receive different priorities for execution. When multiple SRs are present, WLM will work to ensure any given SR is working on a given service class. That topic gets a bit more complex and is beyond the scope of this document. Tech Doc WP101532 covers it in much greater detail. The other thing the WLM classification allows is the use of the new granular RAS feature. That's next. WAS zOS version 8 introduced a function that leveraged the WLM classification file to drive WAS operational behavior down to the request level. The bullet list on the lower left of the chart shows what functions are eligible for assignment to the request level with this new function. Before this function became available, the most granular you could get was by application server, but that meant two applications with different functional requirements could not easily share an application server. The settings shown on the chart were granular only down to the server level. Therefore, the tendency was to host one application per server. That worked, but wasn't the most efficient use of system resources. With this function, again available in version 8 and above, the ability exists to have those WAS settings apply to the individually identified request. Now applications can be combined within an application server and those settings can be managed separately. It doesn't have to be different applications. Some applications have subsets of function you may wish to manage differently. As long as you're able to identify a request, the chart's showing by HTTP URI, but there are many different ways a request can be identified, then you can assign these different granular RAS settings. zOS is a shared resource operating system environment. The broad objective is to most effectively share applications within the common resource pool. This granular RAS function better enables resource sharing at the application server level. It does this by giving you the ability to define WAS behavioral control settings down to the identified request. Applications may now be combined within an application server, but controlled with different settings. This allows better utilization of system resources and more effective sharing of an application server by multiple applications. The zOS operating system provides the ability of one address space to communicate with another without having to use networking protocols. This cross-memory communication has been available since the very early days of zOS and is widely used by many components on the platform, including WAS-zOS. The most obvious benefit of this is low latency in the exchange, since the amount of code exercised is often less for cross-memory than for network exchange using TCP/IP. But with today's high-speed networks, the benefits of cross-memory reduced latency, though still present, are not always compelling by itself. That's why it's important to consider the other benefits as well and view the benefits of co-location in total. The chart offers a list of the other benefits, and the list leads off with the secure nature of the exchange. There's no possibility of network sniffing with this exchange because there's no network. There's no possibility of anyone seeing the information except the two address spaces in the exchange. Elimination of encryption reduces overhead, which increases efficiency and throughput. The cross-memory exchange also allows the assertion of the identity of the execution. This eliminates the need to create identity aliases or work through issues of digital certificate coordination. When all the value statements on the chart are considered in totality, the value of co-location with cross-memory exchanges becomes more clear. Co-location is about more than just reduced latency. The previous chart spoke of the benefits of co-location using cross-memory exchanges. A common pushback on the co-location story was the potential loss of availability if the data system behind WAS-zOS was lost. For example, if the architecture relied on JDBC Type 2 cross-memory to reach DB2, and the local DB2 instance is lost, then WAS-zOS would have no data access alternative. The argument was that a network data access design provided greater flexibility. That line of argument had some validity. To address this, a new function was added to version 8. The new function is available on WAS for all platforms, but it has particular benefit for WAS-zOS because it provides a means of using co-located cross-memory with failback to a network exchange. This function is known as alternate JNDI failover because it provides the ability to define an alternate resource JNDI that WAS will fail over to in the event GET connection failures occur on the primary JNDI. This is transparent to the application. There are many details to this not covered on this chart. For example, the ability to define a threshold for failures on the primary JNDI before failover occurs, and the polling interval used to see if the primary has returned before failback is processed. It's a very well-designed new function. On zOS, the function is extended to include additional capabilities beyond what's found on the other platforms. On zOS, the operator modify command may be used to manually exercise the failover to the alternate and manually exercise the failback to the primary. The reason this is important is because planned outages for maintenance are a key part of the overall high availability story. The ability to issue operator commands to route work away from individual components in a solution topology gives you the flexibility to do maintenance on a granular basis. With this new function, the pushback on cross-memory and co-location is reduced and possibly eliminated. This allows all the benefits of cross-memory communications and co-location for the primary connection, but with a defined alternate failover to a network-based exchange to a surviving resource manager on another LPAR within a parallel sysplex. This new function is a natural fit within the overall HA story. WAS-zOS offers another exclusive cross-memory exchange mechanism in the form of WebSphere Optimized Local Adapters, or WOLA for short. The key thing about WOLA is that it's bidirectional. That is, it supports exchanges that are either outbound from WAS-zOS to one of the systems shown on the chart, or inbound from one of those systems into WAS-zOS. The bidirectional nature of WOLA is unique. The other cross-memory exchange mechanisms, such as JDBC Type 2 or KIX EXCI, are outbound from WAS-zOS only. Note, the inbound capability is particularly interesting because the need to drive Java EJB assets as part of a batch or KIX process is becoming more common. Many software vendor solutions are now packaged as Java EJBs, and accessing that from outside of WAS implied using network-based mechanisms such as web services or messaging. Those work, but carry with them processing overhead WOLA does not. WOLA supports two-phase commit processing from zOS into and from CICS and now IMS as well. Identity assertion is supported in certain use cases. In other words, the bullet points we showed on the earlier chart as benefits to cross-memory co-location apply to WOLA as well. The programming model for WOLA has several different flavors depending on the solution design. Java programs in zOS seeking to go outbound to CICS or IMS or any of the other supported external address spaces use a supplied JCA resource adapter and the methods on the common client interface. In that sense, outbound is very much like outbound using any JCA adapter. If the outbound target is a program in CICS, it's possible to shield that target program from any knowledge of WOLA by using the supplied link server task that installs in the CICS region. The same holds true for communication with IMS programs. WOLA over OTMA implies no knowledge of WOLA by the target program. When the communication flow is inbound to zOS, then the target Java program must be a stateless EJB that implements a supplied WOLA interface. It's quite possible to code that stateless EJB as a thin shim that then invokes another EJB in the same JVM. That's how third-party software solutions can be shielded from WOLA. Finally, a set of native program APIs are supplied for cases where the external program needs to use them. The APIs supply the means of registering and communicating over the WOLA interface. See the WP101532 tech doc at ibm.com/support/techdocs for much more on WOLA. zOS is both a transaction manager and a resource manager. It may initiate transactions or participate in them. When a solution design involves transactions between zOS and data resources, then something has to understand and coordinate the transactional states. On zOS, there's a function called RRS, Resource Recovery Service, that serves as a transaction logging and transactional sync point coordinator. It's been part of zOS for a long time and has been used by key resource subsystems such as DB2, CICS, IMS, MQ, and zOS for many years. RRS is sysplex enabled. The transaction logs are maintained in data structures in the coupling facility. That means transaction managers and resource managers on any zOS system in the parallel sysplex may access the transaction information and perform transaction management. That's a key part of the high availability story for zOS. A highly available design is more than simply duplicated application servers. The ability to recover transactions left in an in-doubt state is an often overlooked aspect of HA. That's because data resources, such as rows in a database table, may be locked pending resolution of the in-doubt transaction. Other transactions may continue, but anything that seeks access to that locked data resource will be inhibited until the lock is released. Therefore, the ability to quickly and reliably recover transactions is a key part of a highly available design. Data access mechanisms that use network protocols use XA partner logs for distributed transaction management. That mechanism works fairly well for steady-state operations where transactions are completing as designed. But the distributed partner log approach tends to work less well when rapid recovery is called for in a high-volume HA design. RRS is a proven mechanism for rapid recovery of transactions in a clustered environment. It's built on parallel sysplex. zOS is fully aware of how to work with RRS, as are the key data subsystems shown in the chart. Therefore, when zOS is combined with those data systems in a parallel sysplex, with RRS serving as the transaction sync point coordinator, effective, efficient transaction processing and transaction recovery is available. zOS makes extensive use of SAF, with either RACF backing the SAF interface or a product from another vendor, for its security infrastructure. One element of SAF is user IDs and passwords used for authentication. zOS can use SAF for that, or it can use LDAP, or it can use both. zOS is not limited to using only SAF for its authentication data. That's an important thing to understand because some application solutions may require extensive authentication lists that administrators may not wish to load into their SAF product. That's okay. zOS can be configured to have separate security domains, with some authentication performed against SAF and some against LDAP. Beyond authentication user IDs and passwords, SAF may also be used to store digital certificates used for identity assertion and encryption. This eliminates the need to have separately defined key and trust store files. The zOS supports that as well. Again, certificates are not limited to storage in SAF only, though there are good reasons to use SAF for that purpose. zOS also uses SAF for many aspects of its infrastructure security, such as the assignment of user identity to the created address spaces. This can be extended to include optional security definitions, such as the protection of the TCP ports so that only the WAS servers can use them. SAF and the product that backs the SAF interface is more than just an ID password repository. It's a complete resource access protection mechanism. Those resources protected by SAF may include nearly any type of artifact on the zOS system. The jobs that create the WAS zOS runtime will create the required security profiles for the WAS zOS infrastructure. From there, you may extend the use of SAF to include authentication data, application role data, or other security protections. As mentioned earlier in the presentation, SAF offers a consolidated security interface with strong auditing capabilities and a history of careful change management. That's why security on zOS is cited as being so strong, because the tools support strong security and the culture of careful security practices on zOS enable it. As noted earlier in this presentation, SMF is a facility on zOS for the recording of activity and usage information. The data captured using SMF may then be used by reporting tools such as RMF or other vendor packages for the purposes of capacity planning, trend analysis, performance tuning, or chargeback. SMF provides the interface for activity recording, and it's up to the various systems on zOS to take advantage of it. WAS zOS takes advantage of SMF by writing Type 120 Subtype 9 records, which record extensive information about each request received by WAS zOS. The chart provides information about some of the data that's collected. The WP101532 TechDoc at IBM Com Support TechDocs provides even greater detail. WOLA, discussed a few charts earlier in this presentation, introduced the need for another SMF record for outbound calls from WAS zOS. The SMF120 Subtype 9 record captures information about inbound requests to WAS zOS, and the SMF120 Subtype 10 record captures information about outbound calls over WOLA. The 120 Subtype 10 record includes a correlator token, so SMF information for the outbound WOLA calls into CICS can be correlated with the KICS SMF Type 110 records that handled the request. Effective management starts with sufficient information on the activity within an environment. That's what SMF provides. Detailed, in-depth information about activity within WAS zOS and other components on the zOS system. That information provides the source for analysis of the environment, from which conclusions may be drawn about what has taken place and what's likely to take place in the future. Absent detailed information like this, such analysis would be mere guesswork. With SMF, it's not guesswork. It's based on extensive information captured for the activity that occurs on the system. A feature of the zOS operating system is an interface called Modify that can be used to change or display information about a running program. WAS zOS leverages the Modify command to give administrators the ability to dynamically alter the runtime behavior of an application server, or to display information about a running server. The chart shows some of the options, but not all. The Info Center provides the complete list. When we discussed the alternate JNDI failover feature a few charts back, we mentioned the ability to use Modify to fail over to the defined alternate resource and fail back. That's an excellent example of how Modify can be used to dynamically alter runtime behavior. That Modify failover failback mechanism is completely transparent to applications running in the server. Another important Modify command provides the ability to turn off the listener ports of an application server. The server still operates and the in-flight work still processes, but the server ceases to take new work. The benefits of that become clear when we think of a highly available environment where we're preparing to shut down part of the topology for planned maintenance and we wish to drain work from a server. By pausing the listeners, the server is viewed by work distribution functions as no longer operating, even though it actually is. Work goes elsewhere. The display parameter for Modify allows you to see inside the running server and see information on settings, on JVM heap, on the status of work, and threads, as well as many other options. Modify provides a facility to minimize and possibly avoid server outages when runtime changes are called for. The Modify interface of the zOS operating system is yet another example of how WAS zOS is leveraging the platform attributes to the benefit of the applications that run on WAS zOS. One of the more popular add-on functions to WAS is Compute Grid, a means of running Java batch jobs within the Java EE framework of WAS. Starting with WAS 8.5, the Compute Grid function has been incorporated into the WAS Foundation. The question is naturally asked, why Compute Grid on zOS? And the answer, just like for WAS itself, is because of zOS. Compute Grid could be thought of as an application constructed to run on WAS, though it's more sophisticated than most because it has hooks into the administrative console and other points of deeper integration into WAS than most applications. At any rate, the same benefits we've been discussing up to this point, accruing to applications from zOS and WAS running on zOS, apply to Compute Grid as well. There are several points of specific zOS integration by the Compute Grid function. WLM classification of submitted batch jobs, the extension of the SMF120 subtype 9 record to include batch job information, and a means of integrating compute grid with enterprise scheduler functions such as the IBM Tivoli workload scheduler. All these things are detailed at the WP101532 tech doc at IBM Com Support Tech Docs. These functional add-on products, Compute Grid, Business Process Manager, Optimized Decision Manager, all act as applications on top of the WAS zOS Runtime Foundation. This entire presentation is designed to show how zOS and the integration of WAS zOS into the attributes of the platform accrue to applications. All those value statements apply to the add-on products as well. The Liberty profile is a function added in WAS version 8.5 for all platforms. It's a bit of a different discussion from the previous charts in this deck. That's because the Liberty profile server model is a single JVM model, not the multiple JVM model we looked at earlier. The philosophy behind Liberty is to provide a server runtime that is lightweight, with those functions loaded into memory being only those necessary for the applications to be run. Further, if new functions are called for, they can be added dynamically rather than requiring a server restart. This is in contrast to the traditional full-function Java EE model, where all the function is loaded whether the application requires it or not. Liberty Profile in zOS has several extensions that do take direct advantage of the zOS platform as shown on the chart. Applications that run in Liberty will run in traditional full-function WAS. The reverse is not true, however. Applications written to take advantage of function in traditional WAS may not run in Liberty because Liberty is a functional subset of the full-function WAS.